Okay, testing. So this is the third lecture on the Fang Robotics Summer 2025 Programming Series. And today we will be doing a recap before we go into analyzing code bases. The code bases we will analyze are that of UT Stampede, because they're really good friends and we like how their code base is done. And then Fang Robotics MCB 4.8, which was the one that we used in competition. And so we will be first doing an understanding portion, then we will be doing an analysis or critique portion, seeing what's the good, what's the bad, what's the not so good. But first, let's go back into Taproot. So if we open here, Taproot, this is the library that is honestly been, I wouldn't say a holy grail, but it's really helpful. It's very useful. And if you're a first year team, or even if you're a much older team without Taproot, this is just been very robust. So Taproot is not only a library, but it is a framework for writing code for the RoboMaster competition. As you can see, it provides first drivers, so it's common motors, controllers with the remote, and the referee system, which is infamously obscure in terms of just how it's documented, the different signals it can send, because it is designed, the whole protocol is designed to send information on 14 robots, and so they've been able to work really hard at making sure that we can communicate with that. And then an organizational framework and round-robin scheduler based off of FIRST. FIRST is a high school robotics competition, and the building blocks is you can have subsystems, you can have power limiting, you can have filtering, smoothing, and computational helpers such as angles and whatnot. And along with that, you have commands and subsystems and command mappings. So, the three building blocks, in short, of Taproot are drivers, the subsystems, and the commands. And when I say commands, that includes the commands themselves, the command mappings, and of course the command scheduler. Usually you don't have to worry about the command scheduler. It does stuff for you. It actually not only schedules the commands, but the subsystems themselves, because the commands act on the subsystem. So if we go here, why do we have subsystems? Let me go to... So a robot contains a lot of components. The chassis alone contains 4 motors. And there are drivers where you can pretty much say, motor dot set desired output, and then something like this, and it'll put that type of strength. But obviously, once you include the turret, that's around 8 to 7 motors, and it becomes very unwieldy to manually handle each motor on their own. So a subsystem allows you to wrap motors, so you can say, I'll say quad drive, and I could say set wheel speeds, and then you can provide desired speeds this way. Or even better than a quad drive, we can say mechanism drive dot set translation 10, 20, whatever. And instead of you worrying about the individual mathematics for each wheel, you just tell the mechanism drive to move in this manner. And for those of you who are new to robotics, this is what a mechanism drive looks like. So as you can see, this mechanism drive has wheels which are angled, and the reason why they're angled is it allows you to do translational and rotation motion at the same time. So that means unlike a car where you're stuck forwards or backwards or whatever curve you're on, you have the full plane of motion at any time. You don't have to rotate to move in a specific direction. You can just slide in that direction. So I guess to show what that looks like, because this is one of the most common building blocks of a robot, is something called a holonomic drive. Let me just go into the right part. Introductions. So if we copy here, this is footage of our robot. And so there you go. That is what a mecanum drive allows you to do in a controlled manner, which you usually can't do with a Ford F-150. So it is important to note that the purpose of a subsystem is to provide you, which could be analogously regarded as an interface in terms like if it was a vehicle, you'd have the wheels, you'd have the acceleration pedal and the brake pedal. So you have all these buttons, because so instead of having to worry about how the engine does stuff, you just worry about the acceleration pedal. The car still needs to do things. So in order to do that, we have these things called commands. If we go here, a command will take in any subsystem, and then it will tell the subsystem to do stuff in whatever way you desire. So if we go here, we'll go on a very simple command. Or let's go to the shrieking command, because that's fun. You can see here, if you don't know C++, it might look complicated, but as you can see, it takes in something called a holonomic subsystem. There is a technical definition, but for all intents and purposes, a holonomic subsystem is something that can rotate and translate at the same time and pretty much do this cool thing. There is a mathematical definition. We don't have, that's outside the scope of these lecture series. If you go in the implementation, you don't need to understand C++ to necessarily know what's going on, but it is taking the holonomic subsystem and it is telling it to do stuff. So every time this execute function is run, it cycles and tells it after it's calculating these values. And so you have various commands. So right here we have the field drift command, where it basically has it move in relation to the field. The counter-strike command, which not only takes in a holonomic subsystem, but also a gimbal. And what the gimbal shows is which way the turret is facing. And from that, it's able to have the robot, so if you tell it to move forward, it will be in whichever way it's facing versus relative to the global field. And then there's more. But the point is, the command allows you to bundle behaviors, while subsystems have you bundle parts and how you interact with those parts. So you can liken a command as to a set of GPS instructions, while a subsystem is just, having a car with a steering wheel and brakes and acceleration pedal. On a computer, that would be like you have a screen, you have a keyboard, that's your interface, but what's the commands? That would be your shell scripts, that would be your, programs. So then we went into programming practices, like using Git to manage versions to make sure that you have a lot of save points in a video game in case coding goes wrong, because coding often can and will go wrong. So it is useful to go back in your work if you have to abandon ship, because there will be nights where you kind of get frustrated and then your code's just a mess and then you cry, but then you realize you're using Git and you still cry because it's Git, but then you realize you can rewind and then you're not crying as much. Next, learning principles such as The Pragmatic Programmer, great book. Solid, which is how you organize stuff more modular, refactoring, which is just simply the art of tidying up your code. Design patterns. These are very useful ways of structuring code for given scenarios. Avoiding golden hammer syndrome, which is needlessly applying design patterns just because it looks fancy. And then optimizing only when needed, because when you optimize code beyond the original instructions, you usually have to add extra construction instructions that's outside the domain of the code. That sounded really technical. Basically, for example, common optimization, let's say you have a program that computes prime numbers, or the factorials. So it just has to multiply 1 times 2 times 3 times 4 and return that number. An optimization is, instead of doing just that, it can store the results. So if it's been called again for something it's already calculated, it can then retrieve it. Even though it makes the function faster, now you have extra logic you have to maintain. And usually when you get into really, really intense optimization, you have to do really weird things, and you have to put a lot more comments. So optimize only when needed, because optimization is a lengthy process in and of itself. And how we prove it, and this outside of the scope of this lecture series, is you use something called a profiler, which is an overglorified timer to see how fast code and what section of the codes are fast or slow. Of course, documentation is an important part, and that includes traditional documentation, and then there's a new trend called self-documenting code. And what is self-documenting code? As we go here, this is in a bit of a mid-refactor, but control, chassis, drive, holonomic. This is the old subsystem. So if we notice here, of course, that's why it's called the old version, because we are refactoring this. These functions have no comments, but these functions do. And of course, this function gives you context, like counterclockwise is positive, because when you go into all the other code regarding the rotation of a holonomic subsystem, positive is clockwise, so you don't have to multiply it by -1. In our code, we stick with mathematical convention. It's not that computationally expensive to multiply by -1 in order to have a, mathematically consistent convention with regards to rotation. But if we see here, update ramps, sync logic to ramps, sync wheels to logic, update field angle, set PWM frequency. As you can tell, there are 0 comments, but you probably know what's going on. When we go in here, in the refresh function, update ramps. So what's the first thing it does? It updates the ramps, and on refresh, all these are called. Most teams and will generally dump all of their code in the refresh. What I like to do is, even if it's just one thing, I give the name to what it's doing, and then define that function. And if you're worried about having it difficult to actually inspect the logic, well, this is now containerized. Everything is its own chunk and bundle. You can press F12 if you're using VS Code, and you can jump to the definition. Notice here, sync wheels to logic, because there's a lot of things going on, sync logic to ramps, update the ramps. Like that's, if we placed that there, it would have been a much longer function. So that is what self-documenting code looks like. It's writing things and bundling things, because I know sometimes you're taught that functions are for things that get repeated. Not necessarily. Functions is just a meaningful bundle of code, of instructions. That's it. So even though these are only called once right here, they're bundled because it's a meaningful bundle. Update ramps, sync logic to ramps, etc. The final part is unit test, which is actually a form of documentation in and of itself, but the reason why they're And a category of their own is because you have code that tests code. And sometimes it has a bit of a learning curve. It can feel tedious, but a simple one would be, show here, test control. Let's see, quad drive. Quad drive chassis. So if we see here, it shows how the code is expected to be used, and then you have cases where you give an input, an expected output, more input, etc. And the reason why that's important, so this is mid refactor, so I'm not sure if this will compile because I was refactoring last night. But anyways, let me pull up actually if it'll show us the terminal. That's a no. Let's go in GitHub. So if we go here into branches, we have unit test. So if we see here on the test portion, it compiles it, and then it runs all of these unit tests, and if any of them fails, it'll tell us, but obviously it all passed. 141 tests. Ideally speaking, you want every line of code to be run in a unit test. Practically speaking, you want at least the complicated functionality to be unit tested. If you're running short on time, or if you're still getting the hang of how to write unit tests, do priorities. Maybe do some simple stuff like setters and getters to get the hang of it, but I would recommend complicated stuff like a class that manages mecanum logic. So at least you know that the motors are being sent the right mecanum logic. You don't have to use print statements, or in this case, the debugger, because there's no print statements in embedded until there is. So that is what we did last. And of course, as much as it might be useful to go in depth what these are, the point of this lecture is a recap of what we've covered in the past few weeks, so that we can see them in practice on actual code basis. Because I can talk all day about what solid is, or what design patterns are, what refactoring, or why we need refactoring, or we can actually look at an actual code base and see them in action, or stuff that might need them. And it goes the same with Taproot. I can talk about these three things like for the next 4 hours. I can go into the different ways to use the drivers, but it probably will make more sense when you see a fully fledged project such as UT's or ours, ACC's code in action. So final thing is with conventions. So as you're aware, programming can get very heated if you ever get into the programming community. And the reason why it gets heated and people make a big deal of it is because they don't have lives, and that's really all they have going for them. So, for example, programming brackets. There is a war. There is a literal war on how you do brackets, indentation style. You have this style, that's almond, that's my favorite. You have this style, which is the GNU. This style, which is Whitesmith's. This is very common, K&R. It's also called, Strustrup. I don't know if I'm pronouncing that correctly. But the creator of C++ does like what's something called K&R. And their reasoning is that this wastes a line. I don't know what's going here or here, but there's different ways to write code, as you can see here. This is another fun bracket convention. This is not used a lot, Oh, it's not even C++, but the point is, people will get heated, and it just depends on what premises you're going on. So I would warn, do not get stuck in a programming debate until you figure out if you are arguing on the same premises. Because my premise on this is readability, while their premise is compactness. So while my premises on what is better points to this, their premise will point to that. So when you are trying to argue on the basis of one ideology and the basis of another, it's like a hollow earther and a flat earther having a debate. You will get nowhere. You might fall off the edge or into the hollow portion of the earth, who knows. But conventions, variable names, whatever, that's chosen by the lead developer. There are obviously, there's a point where conventions can get weird, but if there is good reasoning and it actually has a good effect, and also if you're not the lead dev, just go with the flow. If you want to do a programming coup, that's up to you, but that is what I'm going to say with conventions, because as we go right now to code-based analysis, our code base right now, what it is evolving into for version 5, it is, I will say, there's always controversies in the community. We're aiming for modularity. We're aiming for maintainability, testability. We are aiming for essentially being able to support 7 types of robots. And of course, each of those types of robots might have different versions. So how do we prevent the code from getting too entangled? That's using stuff like solid. That's like using stuff like dependency injections, making interfaces, for which those of you are new. Essentially in programming, it's like you have a British plug, you have an American plug, you have a Mexican plug-in plugging into a wall outlet. So you create an interface, and anything that uses that interface can use it. So it doesn't matter if I have a laptop, I have a mainframe computer, or I have a TV, I have a death laser. If it uses the same plug as an American outlet anywhere within America, I can plug it in, and it can be used without having to reinvent the wheel. So if you notice, even though we had something called like a chassis subsystem or mechanic subsystem, it's something called a holonomic drive, which is just pretty much for the purposes of this competition, anything that can slide around. As you can tell, this is mid refactoring. Like, I'm still writing stuff from last night. You will notice that there's a difference in how commands are written from this version, which is what version 5.0 is going to be, and what 4.8.0 was written as. For example, this takes something called holonomic subsystem. I stands for interface. Holonomic subsystem is a subsystem that's holonomic. So if we go into here, that just pretty much means, if you don't have to understand C++, this just means this can be used as a holonomic subsystem. And then right here, if we go here, this too can be used as a holonomic subsystem. If you program Python, you probably might say, wow, what's the deal? If you program Java, you understand its interfaces. C++, we call them abstract classes. And simply the point is that you can pretty much feed stuff with varying different logic for the same thing. It could be a death laser even, and it just can be used without having to Control-C, Control-V, because 2 lines are different in the code. Other teams might not have that as a priority, and that's all right. But as we are teaching this lecture series for code that is well documented, maintainable, flexible, when I give insights, it's not to diss any team. It's more that we've chosen this modality over another modality. And then the final thing is, obvious stuffs, because as you've been taught in programming, there are things that we have a consensus on. We might not, as the community of programming might not have in the past half century decided which bracketing style is the best. I think almond's the best, but we have determined consensus on some things, like, bad names, global variables, etc. That is something we do have a consensus on. So I will probably say something about it, because this is, for those of you who don't know, this is a community college, and just because a four-year university is doing something in one way does not necessarily mean it's the best way. Our aim is to always be the most organized, understandable code base in RMNA period. And obviously, some people might say performance everywhere, so they might employ a lot more rigid constructs to get that performance. They might even employ assembly code. In that premise, our code base is not the best. But again, our premise is modularity, understandability, testability, and stability. So first code base is not ours. We're actually going to be doing University of Texas. As they are our very good friends, we are going to understand literally how their code base works from the ground up. Actually, let me do this. Hold up, let me see the git stash. Darn it. Let me just check something. This is Mechanism subsystem test. Oh, that's what's not compiling. So if I do this, no, it has multi-line comments. We'll have to do this the fun way. That should have no errors, I think, yeah. Let's see if this compiles, because I'm going to have to commit this to stash it, because we are going to be hopping around to a different version of this code base. And I'll be able to use git rebase to change the commit name. Error. What do you mean? I literally removed it. Oh. I literally deleted the function, or the whole thing, because I know it's not going to compile. Stash, use stash, mechanism test. Let's put a hack. Rename with git rebase shy. Okay. That's why you have branches. So this one is stuff that's being worked on. This is stuff that's in development but's been verified. So we can always go back to here. I believe I have UT's code downloaded. CD RoboMaster git pull, git fetch. Let's see if there's nothing to fetch. Git branch. Okay. So we're going to close this out and then write code. Yeah, I trust UT. I trust. Do y'all trust UT? Bad choice. No, I'm just kidding. So, UT's code base, I guess some interesting fun facts. So their code base is around 5,000 to 6,000 lines of code. Not only do they have a code base, but they do have something called continuous integration. That is something this lecture does not cover, but since it is part of the repository, what continuous integration is, if we go here to build all, is that every time something happens, a specific event like a pull request, which is, if you're new to coding, it just means, it's just the term we use for GitHub, that I want to make a change to the code, so they have to fill out some paperwork and, have a back and forth. So they have a review, and also they have automated testing. Usually you want first the code to actually compile. So if they have compiler typos, syntax errors, then you'll know immediately. You don't have, for every pull request, you don't have to upload their version of code. It's automatic. And then other quality stuff like their linter, which I believe was, the linter did like that one. That's cool. This is a bit of a learning curve to do, to work with continuous integration. So that is why it does deserve some note into their code base, that it has infrastructure, pretty advanced infrastructure. Now, okay, that's cool. Let's go in. So in order to understand the UT code base, hold up, let me get submodule update init recursive. Okay, sorry, notice this was blank, so. Oh, it just means that if you have a submodule in a submodule, it'll also do that too. So it makes sure everything's downloaded, because you can. From that point down. Yeah. So let's go first into, let's see, RoboMaster, UT RoboMaster. That's their project name. So as you can tell, this is another Taproot template project like ours. University of Washington, ARUW, has been amazing at providing resources for the community. And I always like to take time to be grateful for that, because it did make us not have to deal with a lot of, what's the nicer word? Of messes, because programming can get very messy. So they dealt with a lot of the low-level stuff, like how do you talk directly with a motor, sending ones and zeros, because it's so low level. It's pretty much like, I think pretty much if you go lower than that, it's whatever's between that and assembly, or assembly itself. But that's what Taproot does. So what I like to do when I'm analyzing code is I first go into main.cpp. And for here, we notice that they have functions defined. This is part of the template project. We've actually refactored these away into the drivers, because we're more on the object-oriented side. So what that means is, instead of this, you just say drivers.initialize, drivers.update, versus taking drivers, taking all of its instances and doing it. Because in object-oriented programming, if I ask for money, I don't just take your wallet and take the cash. You give me the cash from your wallet. This is the equivalent of taking someone's wallet and taking the cash for them, because this is the internals of the driver. But Again, different architectures have different things, but that's one thing we've done that is a difference between University of Washington and the University of Texas, because we're more in the object-oriented side versus, I guess, more in the traditional functional programming using raw pointers. We won't get too much into the debate between that. In our code base, we only use smart pointers or references. If it's not responsible for deleting data, it uses a reference. If it's responsible for deleting data, it uses a smart pointer. If you're working with a raw pointer, I think we only have the cases in unit tests just to make things a lot less duplicated with how smart pointers work, but that's a different topic to really discuss. But the point is, they have these functions described, and then we have main, everyone's favorite. So they have robot control. So important thing to note, in the template project, robot control is placed here. This will actually lead to a stack overflow. Robot classes, these contain all of it. Your commands, your subsystems, your drivers, serial communication, if it's doing stuff with computer vision. It will crash it because this is allocated on the stack. There's 3 types of memory in C++, static memory, stack, and heap memory. We won't go into details what they are, but the largest ones are static and heap. The smallest one is stack. And we ourselves, our code base, dealt with a crash because I'm actually going to submit a pull request to have the template updated. But other than that, good choice. Very good choice. We see that it creates a drivers instance. So if you can kind of glean off, so drivers is pretty much, as we mentioned in a few lectures ago, just like how C++, when you're starting a code, you have like std cout hello. Instead of having the output as text, what if your output could be sending signals to motors? Or what if your input, instead of keyboard terminal input, it can be from a bunch of sensors? This is pretty much what it is. So they create, hold up, they declare, usually, okay, let me just check. Okay, so usually you do not want to do this in C++ because this is saying a variable of type drivers named drivers exists. Whatever is written on the RAM, so it will allocate memory, and then whatever's written on the RAM, when it tries to read that, it will pretty much read whatever was last written to RAM. If you're lucky, you get people's passwords, but we won't go there. But there are, the other half the time it's inconsequential, but you want to do this or this just to make sure to explicitly make it default, or, well, uniform bracket initialization, because anyways, so here you initialize a robot, you give it the address to the drivers. It's named control. So let's go into main. So board.initialize, board is, well, I guess the board itself. So this is all your pins, inputs, and outputs. Taproot works with another library called modem, which is a hardware abstraction layer. Fancy word. All it means is instead of having to put this random like pin in, pin out stuff, you can just say like leds.init. So it saves you a lot of time. They work with I2C, so they'll initialize on the board singleton. I think, is that singleton or, oh, it's just a whole. Anyways. And then control, which is the robot. In other code bases, this is called robot, but they chose control, which, depends on what you're trying to describe. This is only for one robot, so control. So that's, I'd say, pretty fair naming. And then they declare a periodic millitimer refresh timer with refresh period. You don't have to understand what C++ is, but it's a timer. They're setting up a timer. Ah, fancy, I see. Or old school. So it's kind of interesting program languages. There's different ways. So in the old days, to be more, I guess, to save ink on the source code pages, they'll just put like 1 because 1 evaluates to true. If you want to be hippie, you could even put 3.14 and that would be cast to true. Because basically anything that's 0 becomes false. If it's a string, it's true. But anyways, that's just, I might get fancy with commenting on style because there's, people are new to the programming world and there's some really fun little stuff like that. So here, profile. So this looks confusing, but really this is the equivalent of just saying update IO address of drivers. The reason why they're using profile is that this keeps track of how long the code runs, and this ties it together. So this has something that keeps an eye on how long it takes for update IO to run. Because they did build in some really good diagnostics. Again, praise to University of Washington on that. And interestingly enough, yeah, they did put it with the drivers, which is pretty convenient. So as you notice, every time this loops, and it loops for eternity, you update the IO. So we run here. What is update IO? Ignore that section. That is only for if you're running a simulator. So this code can be run on a simulator if you want. So it takes the RX handler, pulls the CAN data. So that sounds weird, but if you're familiar with CAN buses like on cars, we use them a lot in robotics. So updates the CAN data. Ref serial, the referee system, updates the referee. Remote, that's your remote control that you use to control the robot, reads the input. And then they also have a custom one. Ooh, that's fancy. CV board. We might check that out later. But it's commented out because sometimes you want to remove code, but if code, it might be added back soon, you can comment it out. There's different schools of thoughts on you have Git or whatever, but that's pretty cool. They have computer vision. What does that mean? They're working on auto aim. Unlike CSGO, auto aim is legal and encouraged in RoboMasters. So we'll go back here. So remember, we've initialized IO, and it just calls initialize on all of the various components and the code that works with the components, sets it up to be run. And then we do update anything that deals with input or output, whether that be the CAN bus, the referee system, or reading. Let me double check this is This is recording. Okay. Let's check if there's anyone in the lecture room. Okay. Sorry, this is I want to make sure this is recorded because I brought all my mic. You could we didn't release the last recording because it was really, really poor quality. It was worse than World War II microphones. So finally, we have refresh timer.execute. So we have one main loop that's updating at the fastest frequency possible. Then we have another one with another refresh period every 2 milliseconds. Or wait. Okay. This will be relevant later, but we'll go every 2 milliseconds. And the reason for that is whenever this is run, it runs a command scheduler, it handles sending CAN data and updating the IMU. And these are components which if you update too fast and it's already in the middle of sending a series of signals, you kind of pretty much just get a garbled message. And then the reason why the command schedulers run at this is probably because since it manages stuff that manages motors most of the time, it doesn't have the motors code get updated too fast while, before it can actually send it. And then finally send to terminal serial. So if you really want to just, understand the overall structure without having to worry about the nuances, this is pretty much what all it does. And I'm just going to strip away all the fanciness. If we go here, update IO drivers, update drivers, command scheduler.run. Wait, can I do something fancy? Let's see. Yes.
Can you show it to us better?
Yeah. Okay, so we got that. And that's pretty much all it does in the loop. So as you can tell in programming, there's an initialization portion of main, and there is a loop portion of main. So, where do we begin in analysis? Now, usually, in a traditional programming analysis, we'd probably go into, update IO, we know that. The custom class robot control is the next one. Actually, I'm going to do something even more fancy. Git restore. Boom, back. Warning, so git restore is a very useful command, but also know that it is a destructive operation, which means that if you restore something that's not supposed to be restored, that data is lost. You will have to rely on memory. Copilot, I hate Copilot. With love. I say that with love. At least in Fang, I guess to preface, our AI policy is like your code will be judged by the same standards, which means that just because Copilot or ChatGPT tells you to write garbled code, we will not overwrite the other code that's been handwritten and well tested for incomprehensible garbled code. I sometimes say that AI programmers who write garbled code are worse than bad programmers because they need a computer to write bad code for them. But, hey, not to get too salty. That is just that to preface. And then our other policies, like if you are using AI and you're spending like a week to get a line of code to work, we will not help you until you stop using AI. We will tell you to keep asking AI because if we give you the documentation, you're using ChatGPT, it hallucinates something. Just read the documentation versus having a machine read for you. In my opinion, it's borderline dystopian, but that's besides the scope of this lecture. So, we could try to hunt for the robot class, like robots, but let's just check robot control. What's that? So we see here that there are 3 robots. Now, this is where we go into design architecture decisions. We use the same architecture decision in programming best practices. You would have a library that is shared between all 3 repositories, or Git submodules, whatever, if you want to tie into a single repository, versus relying on preprocessor macros, then having one large script choose which robot to compile. Obviously, this is a collegiate competition, and also this is what UW has decided was the easier one to do. As much as I am someone, as I've said, you want to have the best code base. This is one portion where I personally am willing to make a compromise, and you just want to make sure you don't make too many compromises in the wrong places, because this is pretty benign in terms of because this is a preprocessor macro. If you are not a coder, all this means is that you can program before your code is even compiled. You can alter your code, and then that text will be compiled. So preprocessor macros alter the text without respect to syntax. So what this is saying is if this is defined target standard, then include the robot standard control, and so on. So it just means include this section of code whenever you are doing. Oh, I'm curious. Robot.
Goes through and just replaces all of that, basically the naming convention.
It chooses which version of the main robot code to do. Before. So the warning on preprocessor macros is they will not have any respect. It does not respect scope. So that means whatever you define is global, which is a double-edged sword. It's useful in some cases, not so useful in other cases. Okay. Let's just say, I wonder if on the VS Code they actually added, because they said you had to like pretty much do this for IntelliSense to change, like hashtag define target standard. Let's see if that does anything. There we go. And preprocessor macros, you can feed it into a compiler like define target standard. Usually, so hashtag define, so if I say this like derp, and then I have in the code target standard, this gets replaced with derp. It's actually a search and replace macro, but if you just say blank, every time you see target standard, it just gets deleted. Or it was the early hack for kind of passing variables around the preprocessor. So you will see a lot of old code bases do this. We quickly developed cleaner alternatives to this because it gets very messy. 1 is okay. When you get to 10, it's painful because every time you have a different preprocessor macro, it creates a different version of code. So if we go to our calculator, if we have exponents, so you have 2 preprocessor macros, you have 4 different versions of code that technically has to be tested and compiled. Once you get to 5, it's 32. 2 to the power of 8 is 256 versions of code, which you technically do need to test. Now, in this case, it's pretty benign because they are mutually exclusive. If one is defined, the other is not. And it's secluded to this single file. So in terms of what Fang will do, we are willing to compromise on best practices just because the code, it's a pretty benign, I don't want to say hack, it's barely a hack is what I'll say.
So we do it like this, that way, so before we compile it, we can change the name at the top there to define the like target hero.
Yeah.
And then we compile it, and then that compiled code is specifically for target hero, overwrites all that with a macro.
Yeah.
Okay.
And it only does it here. Now, UT does put a lot more of these everywhere, but in how we do it in Fang Robotics, stuff like this, we do it just with robots and in limited places with respect to whether or not it's a unit test environment or an embedded environment, because there are different ways to handle, like, literally in our code base, 2 things that need to be handled differently if it's embedded and then what robot type. But other than that, it's pretty benign, and we keep it limited to that versus going on. So no criticism on UT. It's just more like if you're new to programming, this seems easy at first, but once you get to like 10 of these, you will find a lot of hard to trace errors because this is not C++. It ignores any syntax. You could define this, input all of Shakespeare's text, and it will search and replace. That's all it does. Automated search and replace and other cool stuff. So let's go into the standard, because standard's the easiest one. Yeah, that's defined. Okay. So we have a class, standard control. It has common control manual. Let's check what that is. It is a common control. So we notice the constructor of common control has drivers. When it's initialized, let's see, so it's all in one H++ file. Formally speaking, you'd want to separate these, but it's not too much of a big deal. Okay, so first we have chassis, flywheel, turret, sound. I'm sorry, I'm curious. What does sound subsystem do? Oh, it just sets a buzzer frequency. Okay. We are actually, one of the first things we are doing, two things I'm trying to get us to a point to do as a group is write code for Omni wheels, and then also write. So when you write sound on a robot and you try to play music, you use the delay function, but that freezes the chip. You cannot have the robot move and play music, or, well, you could have it move and hopefully not hit something and play music, but that's not the best. So we're actually going to implement a slightly more complicated form that allows it to use to move and play music, because that would be funny as hell. So that's cool. It initializes, it registers subsystems. So this is the beginning of where we're starting to understand Taproot mechanics, the nitty-gritty. There's something called a command scheduler. So as I've said before, command scheduler manages subsystems and the commands that it executes. You have the chassis, flywheel, turret, they get registered. And all that means is now they can do stuff within the environment that they were built for. Next, run out, play startup sound. What is the start? Do they have songs? Do they have... Yes, they do have songs. I don't know what this is going to play, but that's cool. That's pretty cool. We're actually going to have ours use notes, so like A, B, C, D, E, but that is pretty cool. Like, so let's see. So this is an array or something, yeah. But anyways, okay. I'm sorry.
Like showing how much sound, or like I guess like how long each note is.
Let's yeah. So hold on, let me go back. Yeah, sound.hp++, data length, note interval, and data. So they're doing some manual memory management. Pretty cool. Yes.
The other two are just
The data. So 27, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 3. So 27 notes. Note interval 30. And then the data itself, which is a pointer to the first member of an array within this struct. Yes, it is. Let me select configuration. Oh, I see now. Hold up, let me go back. They did program it. We will, hold up. Actually, I'm gonna do this right now. Let me put this on the to-do list. Add selecting specific robot type to configuration task. And we'll put that under P3 and then UTRAS. So select configuration. Now the question is how to UTRS S note UTRS code base. And we'll just go to .vs code. And then what should I say? Keep hardware run and hardware and sim and test configurations. Potentially just split hardware into hardware pierce, hardware devour, etc. Okay. Yeah, we'll add this to the summer refactor. Why not? Feature.
So you just filled out the form for you to tell yourself what to do later.
Oh yeah. We actually took a lot, like UT has great infrastructure, so they're doing this. So I started to do that. We're having 2 projects. Summer refactor. Got a lot of stuff done. But yeah. But that's enough about us. More about UT. But first, I did a hack. So we're gonna do that. Select configuration standard, and let's see if that's defined now. So they use the traditional shout case for or this preprocessor macro. No, it's a constant. So this is a dying convention. It is. If it was up to me, if we were able to make preprocessor macros do something else, we keep the old shout case. And it was, I will say, like I honestly was like kind of like in, I don't want to say the word emotional, but it was a bit of an emotional, like just having to accept that when I was reading different style guides, I was like, and I did encounter in our code base a preprocessor macro collision with 2 libraries that we used, so that is why we chose it. But there's nothing wrong with shout case, but it's if you are in Fang Robotics, we do more something like K agitator. But besides the point, so let's go now here into, first let's go into common control manual again. Common control. So as we can see, it just registers your basic subsystems, and then it runs the startup command, which plays a nice song. So bravo. Now let's go into common control manual. So what I'm guessing is their Sentry is autonomous, so it initializes subsystem, but common control manual will have mappings. So as you can see, there is something called press R toggled, so there's a command mapping. And how command mapping works is there's different types. This is toggle, so if you press the button, it turns it on. When you press it, it takes it off. So you give it a driver's instance, you give it actually a list or vectors of all the different commands you want to trigger, so you can trigger multiple commands. But if it's a single command, you just use this. And then finally, remote map state key R. So as you can see, whenever you press R, it schedules the command move Beyblade. We'll go more into details of some of their commands later, because we do want to get the big picture image versus getting too much of the nitty gritty. But we'll still look at, we'll go stop smell the roses. So now we have command rotate flywheel. So these control the flywheels, move turret, toggle mappings. So you can see here, these commands takes it into drivers, and then it takes whatever they work on. So these need a chassis and a turret to work, and then some configuration variables. So these probably deal with, the mechanism logic, and these probably deal with the flywheels. And what the flywheels are is they're the most common way in RoboMasters to launch a projectile. Okay, so look, command move turret, etc. So that is the common one. So they use inheritance to get these set up, which is pretty cool. That's a cool way that's one of the common ways to prevent code reuse. Now we're going to go into the standards. So you can see there's a really long file, or not really long, moderately long file for the constants, configuration constants. Common control. There's like a robot constant somewhere. Yeah. So they have universal constants and then global constants and then instance-specific constants, configurations. Sound startup is that. Use ballistics, false, ballistic iterations to... This is a lot of different constants, so we'll go into the actual control. So it inherits common control manual. It takes in the drivers. As you can see, like, well, actually, it's pretty compact to where it's not too much of an issue to worry about, like, defining, initializing stuff within the header. We ourselves do as well have exceptions to not defining stuff in the header, such as specific variants on dependency injection components. I probably sounded like I was speaking French, but the point is like, you know, there are cases when you want to break rules, and there are cases when you don't want to break rules, and it's up to a lead dev to use their experience to determine in which manner to do so. So let's see, common control manual initialize. So whenever you inherit a class from a different class, you actually have, like, so all of this, you have it in here. Like, common control manual, it's as if you have an actual, like, instance of common control manual instantiated inside the class. So it has to be initialized, and this does its own stuff. While we're in Sentry control, we want to be in standard. Let's close, don't save. So yeah, it initializes stuff. It has the common stuff. It registers to the agitator. It gives mapping specific to this robot. So left mouse down, left switch up. And what does that do? That controls the agitator. Left switch up. Seems like it activates the flywheel. So that's all nice and dandy. So it initializes. And notice that it has a drivers.command scheduler, and in the main loop, the command scheduler was called. Whoa, now we have a hint of what's the update doing to this robot class. We're attaching stuff to the command scheduler, and when the command scheduler loops and the command mapper listens, whenever it's doing this, it's not technically updating the robot. If it was up to me, the robot itself would own the instance of the command scheduler and the command mapper, but I did have a talk with the devs, and they said it just made it more convenient for, you know, if you're starting out. So, you know, that is one thing we do have it not on P4, just like P5, if we can have the command scheduler on the robot, and the robot says, you know, you have the control, but you'd say, like, you know, control.update. That would have been my preferred thing, but we do use the current schema just because that's what we were given. But that's just some notes in regards to thinking modularity, weighing the pros of cons whenever you are doing a hack or a semi-hack, and so on. So let's go into some subsystems. Okay, so I guess everyone in the room, so it makes sense, right? With a command mapper, it gives you a, let's see, it gives you a command that gets some commands that get activated, and then what needs to trigger the command. And then you kind of feed it into the main system so it knows to look for that mapping. Yeah. Perfect. You can see this is what object-oriented programming allows you to do. It allows you to bundle. You don't have to worry about how it looks for those mappings. It just does it. Actually, no, we're not going to go down that rabbit hole. There's an interesting way of how it does it. And it's like surprisingly does not impact performance. All I can say is that it does it in brute force, and I mean you kind of have to, but it hasn't had any impact on performance, which is kind of cool. And see, they use hashtag pragma once. So Pragma is a non-standard preprocessor macro. Throughout the years, there's different pragmas. The most common is once. So in C++, you want to prevent duplication because it will lead to a compiler error. One way they optimize stuff with compilers is they allow it for majority of things to assume that there is only one and only one copy of said item. So if we go here into Fang Robotics, well, maybe we might switch to Pragma once, but currently, even in Google, the standard and recommendation is to do a manual preprocessor macro based off of where something is in the file tree. But it, in the scope of and what we're doing, it shouldn't make too much of a risk doing #pragma once. But this is technically non-standard. It's because there's different debates on how it should be done. So C++ and C++ added modules. Our compiler doesn't support the module stuff, so we cannot do modules at the moment. That will be slated for next semester. And it also helps us mesh with older code like this anyways in a more unified manner. But other than that, wait. Okay, so there's no header guard. Since these robots aren't instantiated once, the header files do not have the #pragma once. Technically, strictly speaking, every header file should have a header guard to prevent duplication, because the compiler will complain once you have more than one copy. Because #include, you know what #include does? It literally copies and pastes the entire contents of the file right here. And so on. So you have I guess almost 1,000 lines of code by then after you're through all these includes. Because here's the cool thing. Includes can include other includes, which includes other includes. So you can see where the duplication can happen down the really long chains of includes. This is just because it is a bit of an older form of modules. We didn't have the concept of module C++ back then, and we're adding it now. So I don't know. We might switch to modules. Maybe I might wrestle with the compiler. Maybe not. Who knows? But let's move on. Let's go into, well, they use inheritance. Let's go to common control and look at a subsystem, chassis subsystem. As you can see, chassis subsystem is a subsystem that is required to work with a command scheduler. What is a subsystem? What does it do? Let's go to the Taproot subsystem. That's kind of cool. They made their custom subsystem. Hardware okay. It's amputated. Set amputated. I do wish they kind of documented what this meant by amputated. RoboMasters is not a robot amputation contest in the sense we're not destroying actual robots. So that actually does pique my curiosity in what is amputated and why is it, set true or false. Maybe they want mid-competition hot swap or something, but so you have initialize, register initialize, set default command, get default command, refresh. You can see that is just the update function, so it gets called repeatedly. Refresh, safe, disconnect. So this command, refresh, safe, disconnect, means when your remote is disconnected, you can write code that gets called to make sure the robot does not flail around. Very, very useful. Do not ignore. If I were them, honestly, I would have done it like this. So it forces them to implement. But it also just makes stuff easier this way. But let's see test commands. So the main ones in a subsystem, as you can tell, is the initialize and the refresh. And refresh safe disconnect. Initialize, just like in the main loop, a subsystem sets stuff up, and then like in the main loop, it also has stuff that gets repetitively called again and again and again. That's all subsystem does. There is custom stuff with UT, which is all right. Taproot was designed to be extensible like that. And then, so yeah, this is a very cool way, preventing code reuse, adding custom functionality, all for it. So great job, UT. Even having an is hardware okay. That's like robot safety is a high priority in RoboMasters. I will say not all code bases, and that includes ours, at some point did not have robot safety code. But now we do. For the record, now we do. But let's go on. So ChassisSubsystem, as you can tell, what does it do? It creates... Let's actually go to the header file first. So it overrides initialize, refresh, hardware okay. It has a way to limit the chassis power. At brief, update robot motion. So I see. So it does holonomic stuff, translation, and rotation. And that's a vector 2D, a 2D vector. And then a bit of a hack, but okay. It's all right. This one is XY linear velocity translation rotation. But at least they document it, because if they just said this, I would have thought measure velocity is like, is the robot moving up or down? Is it bouncing? But in this case, we know that XY means this and Z means something else. So that is amazing job on documenting that with UT. Next is it has a pointers to the drivers. It got a power limiter, and let's check what a power limiter is. Get power limiter ratio. So this algorithm, so this is a common algorithm. This was initially implemented in, actually I'm curious, was it UW or was it UT? No, it was UW probably the first, but you never know. Because they have their own raw implementation. Taproot has the same algorithm inside here already. So if we go into like control chassis power limiter.c++, where is it? Here. It's written in different forms, but it's basically the same. Essentially, if you go above a limit threshold, it will begin downscaling the wheel speeds, or it sends you a scaling value from 0 to 1 to apply to all the wheel speeds. And then when you get to the energy buffer limit threshold, it returns 0. Because that means because your chassis gets shut down. You used to take damage for exceeding chassis limit, but now it's just shut down. You become a sitting duck. It's very brutal. So as a power, what?
When would that happen? When we're like exceeding this, it's a voltage, right? Or power. So like we're hitting something, or like maybe something got bound.
So let's just say, so when they have an energy buffer, they calculate it in frames. So technically, yes, you could think of it in wattages, but really they give you a budget for energy every like 10 times a second. And then they calculate your wattage, multiply it times time, subtracts the energy. Technically, it is wattage, but since it's 10 hertz, 10 times a second, it's so quantized that you could technically be below the wattage or even above the wattage, and it wouldn't trigger the energy buffer threshold, because instead of, so I guess the way to have the analogy for this is that it's like, let's say you have like a budget for how fast water should flow, right? So you have a rate of flow. The easiest, simplest way is to just say it can't do faster than 10 gallons per second. But in how it is computed on the referee system, it says 10 times a second, there is a limit of 1 gallon. And if in any of those frames you exceed 1 gallon within this second frame, because, you know, fluctuations depending on how things align with these slices. So I wish I could give the simple answer, but as a programmer, we do have to understand that we're not dealing with wattage, we're dealing with energy in discrete frames, because there is, let me see if they have that picture.
So this is something that's thrown on by the competition, the referees.
Yeah.
Okay. So that you're limited the amount of power output you're plugging into everything.
Where is it?
Almost sounds like
Yeah.
you have like an actual battery.
Yes, it is a certified DGI classic. They, even the referees made a emoji. So you will see this as the competition, you know, heats up more and more as people discover more idiosyncrasies. And, you know, it's not to roast them. It's just, you know, like some just weirdness happens and we have to deal with it. So let's go back to, where is it? Chassis subsystem. Okay. So this uses the architecture as set by ARUW Edu, and what I personally call it is a parallel list or parallel struct. So you have 3 arrays of data type 1, like data type B, and then or data type C, and then you're exchanging data between those like 3 lists. And so I'll show you how it looks like in the code. So first, so as you notice, wheels is just a classic array of motors, motor controllers. And then you have target velocities. And then this is what I was saying is that we do not do in Fang Robotics. This is a classic traditional design, you know, I'll say design pattern. I'm curious, those in the room, instead of hard coding with preprocessor macros, what could you do in a class that you don't have to do this? You take it into the constructor and just have a, you know, initialize it with the constructor given value. Like, let's see. I don't want to necessarily sound any too critiquey. But like that is something. If you are programming for Fan Robotics, we will have you redo the constructor, which isn't too hard. It's just because when you're dealing with hard-coded preprocessor macros, because as you have, you know, 1 robot, you can have 1 energy limit, energy threshold. But then once you go to 3, then you have global variables. Like I actually spent like 2 days undoing this sort of pattern in our code base. Like you'll find commits like somewhere in like April or May of 2025 that I do that regarding the chassis subsystem, chassis commands and constants, but you know, to each their own. So these are just energy limiting constants. And then finally a set mechanism wheel velocity. No way. Did they? Yes, they use the same, you know, check this out. So let's go into our code. That's not our code. That's their code. Is this their code base? Oh, this is... Okay, so let's go into chassis. And so holonomic mechanism. In our case, we decided to, since we are very heavy on single responsibility principle, so our mechanism logic is in an individual class, not calculated by the mecanum subsystem. Because the point of mecanum subsystem is to apply mecanum logic to wheels. But mecanum logic is not the simplest, and so if you see here, we use exactly the same research paper. And it's kind of really cool that we have like it, I like to cite stuff in the documentation. So if it's a complicated or a sort of algorithm, send a link. I even have a Desmos link for some of our algorithms that I homebrewed. Anyways, so let's go into the ChassisSubsystem.c++. And we'll see initialize. So standard for loops. Oh yeah, because they're using a raw array. So they're using more C-style stuff. So in our cases, we do stuff with a standard library. We do not mess with classic arrays unless we absolutely have to. And I can promise with a 99.999%, 9999%, so even more than the certainty of the American healthcare system denying healthcare to your insurance claim, that we will probably not need to work with raw arrays with what we're looking at. I don't know if they have written anywhere else why they work with raw arrays, because like they do give opportunities for extracting a little bit more performance, but it does take advanced coding, and the only thing I would say with them is I would recommend having it written somewhere within the documentation folder. Let's see if docs, they don't have the docs, but anyways, that's what I would just recommend when you're doing stuff that is weird, because good writers break rules, but good writers know the rules. And I know UT is filled with computer science majors, and so generally they're taught like that logic. But in our case, and in terms of just evaluating our specific, Fang Robotics methodology, we find the risk of manual arrays and the issues they give to be more, to not be worth the performance gain. But let's see. So if we go into chassis, so what kind of for loop we use here, holonomic mecanum subsystem is, where is it? Oh, quad drive, my bad. If we go into quad drive subsystem, so we have a for loop. So this is a for each loop. And then this has, so it's just saying for each motor, unique pointer of motor to motors, motor.update. So we don't have to worry about the bounds, because in our case, so we use std array. And the cool thing is, I know these have been very finicky in the past, but now you have std span, which you can iterate through an array without having to worry about this number. But again, as I've said, to each their own. The cons was, before I found about std span, is we would have to use template shenanigans to make functions work on arrays. So that's because that's what we're going to use for storing notes in our music code. So right here we have set target wheel velocity. So this is a common pattern in the community. But this is one of the things that you can just make a new class of a wheel that's, goes to a target velocity and having to juggle like an array of 4 wheels. And so in our case, if you see here we'll view the old code. We have 4 drive motors, and in the code, there's no target velocity. All we have to do is set target speed, and that's that. In their case, they have to set the target speed variable, and where is it? Sorry, we've been like clicking around. Set mecanum wheel velocities. Okay. So you can see why this gets in my opinion, a bit more messier. So you have the input, and then it applies the mechanism stuff to the set target wheels, and then let me check each one, because usually they apply PID. Right, so M2 pi, drivers kill switch, refresh, update velocity. Wait a minute. What's the point?
What was with that set active thing?
Let me see. It's update velocity or set active. Oh, it's this one just checks for, this is safety code.
Okay.
So if it's kill switched and is not amputated, let's see. So let's go here to update velocity. So it stores the target velocities in as a variable. Okay, that's cool. I did kind of wish there was a little bit more rough comments, but this is written in a manner where it is self-documenting enough to glean over. So we can see here that it's getting the power limiter ratio, and then it's checking if the power scalar is close enough to 1. And if it's close enough to 1, set it to 1 so it is 1. I'm guessing from my experience, it means that there was a chance due to floating point shenanigans that this could be slightly above 1, and it might trigger an error if it is above 1, depending, if they have assertions. So this just ensures that it is 1 if it is 1. Which, if you're not a programmer, you're like, that sounds stupid. Well, we're in computer science. We're very stupid. But no, this is actually a pretty cool thing that they did, and a nice learning, opportunity for us. So next here, total error. So for every, let's check it. So total error is 0. It checks the total error, so it adds up target wheel velocities and wheels, and then gets the absolute of the target wheel velocities. Limit chassis power. So this is just chassis power limiting. So I guess this is how much the wheels are doing stuff. ABS just basically makes it positive. Wait, target wheel velocity. Is this a delta? Is this the actual definite? Let's see. Let's go closer to the code. So it calculates us basically the sum of the magnitude of all the wheel velocities. I would recommend this being commented on the y, but at least it's written in a way we could get the what. But essentially, I think what they're thinking is that if the wheels are overall spinning more, so they're trying to get a measure of how much motion, how much power is being used. So if a wheel's going forward, that's positive. If it's going backward, that's negative, but that's still motion. That should be added. Why it's called error? Not sure. As you can tell in UT, they like to use copy initialization. In Fang Robotics, we are hipster. We use something called uniform bracket initialization. The what? Oh, yeah, let's see. So for every wheel, total error 0 is equal to compare float close. Use this instead of the equal. So if the total error is 0, so we take the total error. Yeah. So if it's close to 0, if the wheels are basically close to being still, so So this is the classic ternary operator. Very useful if you want to avoid like a lengthy if statement and you're trying to assign stuff. But let's see. Like I like it, I do like using ternary statements where, like this is a pretty cool feature. Not all programmers know this. I mean, some of the older code in Fang MCB, I wasn't aware of the ternary statement, so I had to rewrite it to use this. But the fair warning is make sure it's obvious. If the ternary statement is not obvious, then no. So let's see. Total error 0 equals... I would probably just extract this as a function at this point because they have to, but So the velocity error scalar, if it is 0, so if it is true, then we feed it the 1, so we divide it by 4. Okay, this starting to make sense. So then if we take the target wheel velocity and divide it by the sum of the total velocities, then we have a scalar where we can, because we're applying this to one wheel, but we're working with the sum of all the wheels. Limit value. So we take the scalar and we generate a scalar from wheels, which is 4. So let's say this was 4 divided by 1/4, but then we want to add an additional scalar on top of the power scalar in respect to the total accumulative sum of the... I'm sorry, I'm starting to spit out like a lot of like smart people were. And then this just makes sure that it's within a valid value for a scaling function, which is 0 and 1.
So I guess what that's doing is if there's a need to limit the power of the chases, then it's just figuring out by what scale it needs to be limited. Stuff like
Yeah. So not...
the velocity, like for the movement, it still makes sense if it's scale out.
Yeah. I will say I would like more documentation on why, because this is applying a different power scalar to each wheel. The traditional way is doing it to all of the wheels at once. Now, there is obviously reasons for optimization, so maybe they're trying to put more weight on certain wheels than others, but the reason why you want a uniform scaling is so that it doesn't interfere with the mechanisms. So it's, even though it's translating and rotating slower, at least it's still going to move in the same direction. It's still, when it gets to this point, it's going to still be at the same rotational angular position. But this could be some advanced stuff, and that's pretty cool. So, hardware, okay. So for eye and wheel, so it just checks if they're online. Good. And then input. Let's see. I wouldn't call this input. I would say set motion, in my opinion. Because input, well, actually, input technically does make sense, but this is a physicsy thing. But that's more in programming conventions than actual analysis. Okay. So let's see what it does. So vector 2f. So vector 2f is just an x and y vector of floats. So you have move and then times max linear velocity. I see. So this scales an input, which probably each of those components are between 0 and 1. Spin -1 to 1 in all the components so that they can scale between a max velocity. The angular term, linear term, so we take the absolute value. Okay, so let's check. So angular term, linear term. I see. So we're dividing it by the wheel radius, because we're trying to convert the wheel speeds to wheel velocities, linear and angular velocity conversions. Okay. Overdrive error. Overdrive equals max. Is this a global? This is a global constant. So when you are debugging things in programming, one of the common sources of errors is trying to gain data from the global space versus when you're trying to gain data that is associated with the specific instance of that class. So there were two conventions I was taught. The first convention was this. We're moving outside of that convention. We're doing this convention that was given by Google. The reason why is if you have a private member constant, you still want to tell it's constant. So what I did was I would say MK, which just didn't look, it just didn't look nice subjectively. But here we can just say like K mecanum logic. And it's pretty seamless, and we know that this pertains to a specific instance. Some people will say that this convention is supposed to be used for private members only, which is partially true because usually you want variables to be private if they are a class member. Well, yeah. But the other reason for these, unless you're working with certain exceptions, such as vectors or whatnot, is that if you have a static constant, even if it's private, you do not put the underscore line because that is a global variable. It doesn't pertain to a specific instance. It can't vary from instance to instance of that class because it's static. And static is a very overloaded word in programming, but it just basically says in this case, make a global variable that can be accessed for members in the class. That's all. But yeah, that I would say is the other thing that would be very helpful, because like how they do stuff here is they do use global variables, and when you're trying to have variation, because you can notice that they did have variations in their commands. They didn't have to duplicate the code. Because in competition, it is useful. One time we had the power overflow issue, but then we thought it might be solved. But then if we put the configurations too high, then we're stuck with that. But what we could do too is we just duplicated the instance, fed it different configuration variables, and that takes us 5 seconds. If the global function, hey, nice day. So if it is tied to a global variable, we can't have ease of variation, and you would have to redo the architecture a bit, or just duplicate code with make command ChassisSubsystem 2 wheels 2 or something. But in this case, wheels, is pretty benign. That's actually good for explaining. Was it wheels for wheels? So that's pretty cool. Let's go here. Overdrive error. So linear term plus the angular term minus max wheel velocity. So let's see. This is a constant from the LX way. So I'll actually show you, since this is relevant if you are new to programming. So in this, and we do have this in our code, there's LX, LY. And so when you come to the ones we actually do use, LX plus LY. So that's just LX, the length of X plus the length of Y. Okay. So they're doing a lot of fancy math. That's pretty cool. Like, you do want to try to find a way to have the edge in competition. Let's go into more analysis. So what this is doing, let's see, WZ. What is WZ? It's the spin. LXLY divided by the wheel radius. Oh, they're trying to get the angular rotation. This is I think they're just doing a roundabout way of implementing these scaling so it's actually uses units. Because, for example, in our code base, when we have the logic, so we have a lot of Mechanum logic classes. So you have the abstract logic. So if you do this without respect to radius, your code will still work. It's just that it's very hard to tie it to any tangible value. But if you tell it to move forward by 1, it'll move forward. If you tell it by 2, it'll move twice as fast, etc. It's just you can't tell it to move 2 meters per second because there's no tangible value. So that's why it's abstract. When we had field Mechanum logic, or let's go to robot Mechanum logic, this was where, so we had meters per second, and we used units, and we applied the constants and whatnot. And so you can see, you can see in our style guide, we like to err on the ear of making a name too long than too short. Because even though it might look slightly ugly potentially, this is a pretty obscure function with a bunch of obscure constants, and it helps in the long run versus saving some ink. Oh wait, I need to remove 2 double. Let me put that. So we had to do a hack because with the units library, there is so when you're translating between linear and angular velocity, you can't just multiply or divide by the radius. You have to do meters per radian or meters per radius. Because if you think of it, if you're multiplying, like, let's get linear velocity from radians per second, right? So radians divided by second times meters. Technically speaking, that's meter radians. So the unit you technically want, if you're, pedantic programmers, meters per radians. And so if you divide the angular velocity by the, radius per meters per radius, then it is radians per second times meters divided by radians, and that's meters per second. Yeah. And that's documented in the code. But when we didn't understand this glitch, I did a hack where I just stripped it to a raw double and did weird stuff, but it's no longer needed. So we're actually gonna... So coding is an iterative process. Like, just as we are gonna, I have some stuff to say, good and, critique with their code base, this code base... I'll have a lot to say too. I mean, there's a reason why we've been refactoring it. Like, even though I feel like, it's a very high quality code base, I do want it to be like really geared. Like, I want it to be the best code base. And so that's what v5.5.0. So remove unnecessary 2 double within Mechanum logic classes. I'll just sign myself. Labels P. Yeah, it's P2. No. That's technically a P3. P3 task projects. When I put priority settings, I don't just put it, at least in right now, not with just respect to code functionality, but also code comprehensibility. Because as you can tell, this is a bit of, we've been spending 30 minutes on just one class. And if they did put some comments onto what and why things were being done, it might have taken more 10 minutes. But regardless, their code is, as I've said, self-documenting enough where we can glean from the code and understand. So overdrive error is, let's just see how it's being used. So we want the minimum of the angular term or the overdrive. And then WZ, which is omega Z, so that's your rotation with respect to the Z axis. That's being multiplied by 1 minus the correction divided by the angular term. So I'm guessing if the correction is higher, it scales it down, and then we also subtract the correction from the overdrive, because the overdrive is reused in the linear term, because it has linear term plus angular term. So this is just a manner of scaling stuff. And overdrive error could be they exceed the maximum velocity for a given wheel. Ah, I see now. So there's a max linear velocity, that's configuration wheel max velocity is if the what? Yeah. So that means that the wheels cannot exceed. This is like the wheels should not spin this fast physically, because sometimes the math will make, two wheels stay still and the two wheels to spin super fast. So even though you're going at the same linear velocity at that robot angle, which is diagonal, they will spin much faster than normal. And so that could lead to motor damage or whatever if you... Yeah, so basically, if this is exceeding the overdrive error, it's going to scale it down from what I'm looking at so that the maximum wheel velocity will not... Oh, so this isn't a for loop. So the maximum wheel velocity will not exceed for any wheel. So it just downscales it. That's something we might need to do. So I'll just add overdrive protection. Add overdrive protection. And this will be not in the refactors. P2 could be that. Wheels. Calculate or detect when a wheel exceeds the maximum wheel angular velocity and scale down the entire input so that none of the wheels velocity. I'm not... With our motors, not really. But generally our motors do not go... You generally don't need it, but it's a really cool, it's a nice feature, you're thinking with this. Because again, they use different motors, we use different motors, so this is probably motors that need this to be factored in. Our data sheet is an Instagram chat with the seller. I'm not kidding you. They've been very helpful, but I kind of wish they did have a data sheet, documentation, but you gotta work what you gotta work. They're pretty cheap motors for the power they give, but we're not using those motors for the next two robots for sure. Like linear velocity correction. So I see, because since you can't necessarily scale down the wheels, because you're starting with the input, so they're now scaling down the linear velocity and angular term before feeding it into the set mechanism wheel velocities. Now, I would probably need to ask questions to devs on why they would do it here versus here, because when you feed the raw values here, it gives you theoretical wheel velocities, and you can quickly detect which one has overdrive or which one has the highest overdrive. You get the maximum of that array, and then you figure out the constant to scale down from, how far it is from the maximum. Versus which, I mean, this is still pretty cool math. I mean, the fact that you're able to even predict overdrive before you even calculate the wheels themselves, that is interesting, but that is, in my opinion, a bit difficult to understand. But no, still cool, still cool. Again, there's probably a reason I don't know why necessarily it's doing it in this way, because I like beautiful things in math. Like, I mean, well, it's like, where is it? We did have to use Mecanum information anyways, so we were already calculating Mecanum stuff before the Mecanum stuff, but it's all right. So for those of you who are new to the Mecanum stuff, so in this thing, one thing to know in this paper, x is y and y is x. Just note that. But if we see here, you're right here, or no, longitudinal velocity right here. You're adding Lx plus Ly times omega, Vx minus Vy, 1 over R. And looky here. Minus Vy, Vx, Wz, Lx, Ly, 1 over R, and so forth. And then they even have the inverse kinematics. Cool thing, we too have the kinematics. Well, technically, correct me if I'm wrong, but sorry, I accidentally locked my windows. This would be inverse kinematics. This would be the kinematics, because the wheels are the one doing the motion. So you're trying to figure out what it needs to do the motion. This is inverse. This is the regular version of kinematics, but that's beyond the scope. So right here we have that, and then they rotate it minus 90 degrees. Because x is 1. Well, wait, no. Could that be solved with rotating 90 degrees? Well, but no. So they rotate it to match the reference frame of the robot. They return it. Oh, this is measure velocity. I'm sorry. So set Mecanum wheel velocity. So it sets the target wheel velocities. I'm guessing why they have the target wheel velocities in two ways is because of this. And then they pass it on. So if we're getting more objective, because on objective object-oriented programming, and obviously, they're not as object-oriented as we are, and that's not bad. That's just different design choices. But generally in programming, even though this is not a global variable, in the class scope, it does act like a global variable. You have the target wheel velocities being indirectly set by this, which makes it harder to test this function, because you have to get this variable versus just checking for its return value. And then when we go into refresh, set amputated, so this just checks for whether we should say if it's amputated or not. I think maybe it's like the amputated could mean like safety features, because there are teams known for robots like literally being set on fire. Well, they smoke. They don't, like, in my awareness, they haven't burst into flames, but this could just be a way to shut down, because maybe this was written before refresh safe disconnect was a thing. So set active, so if it's kill switch, so that's safety code, and then update velocity. We convert from radians per second to revolutions per second, and then we limit the chassis power, and then wheels.update velocity. Wait. So the wheels refresh, but are the wheels updated? Or do they even need to be updated? Let's see. So wheels.apply power scalar. Let's just check that function. Apply power scalar. Set desired output power scalar. Float if blah blah blah. Measure position. Is there a PID? Yeah. So I would say position integral derivative control. The way, because in a motor you can't just tell it to go 1 meter, like 1 revolution per second. You can give it a voltage or like a abstract output value, and you could have something that measures the speed. So how do you coordinate the proper output value and the desired speed? One way to do it is if it's far away from the speed, to tell it to give more output. If it's above the output, tell it to give a negative output, and it oscillates like a spring. Integral and derivative are a bit weirder. The second important one is derivative. It acts like a dampener. It goes against the proportional, because derivative is the rate of change. So if it's getting closer to the desired value, the rate of change is negative, and so then that is subtracted from the desired output value, so it's slowed down. But then when it gets very close, proportional is very weak, so it can have a steady state error. So integral multiplies how far it is times the time elapsed. So if it remains long enough, it'll start accumulating a push, and then it just nudges it there. So you'll see it like kind of like go off, and then it will slowly move into 0 error. If that made sense to you, I somehow explained PID in like under a minute.
Kind of like the big picture idea.
Yeah. Okay, that's good. That's good, because I'm like, PID, like that took me like quite some time to like really figure out what the heck's going on. So, and how we do it here with our Mecanum subsystem. So we have Mecanum calculators give inputs and outputs. Let me go to Mecanum subsystem. As you can see here, Mecanum logic returns the wheel speed. So in this code base, let me return. The Mecanum logic would be this, and instead of setting it to I'm just going to call like a class-wide global an instant-wide global variable, it just returns the value to the function that needs it directly. But hey, the code still works. You know, again, like they might have reasons for this sort of structure. And I would say, and this is also in us, we're writing our design document explaining any idiosyncrasies. Because, for example, we don't like, you know, if you know C++, you know about asserts. We have a custom assert called Fang assert. So if it is a unit testing, it does a regular assert. If it is not, it calls a modem assert and gives the file. It gives the file name, the line number, and the description. So we use custom asserts that relies on preprocessor macros, which is non-standard, but you know, we do have to explain why you see Fang assert in all caps, you know, littered everywhere. Because our codes are atomic, where we, you know, if it's below 10 lines, you can't really get more than one assert meaningfully in most cases. But NASA recommends putting 2 asserts per function or more, so that you don't have to do print statements when your code does something wrong. It will tell you that something is violated versus having to go line by line or tracing the whole stack call to figure out if the values are actually being calculated the way you want it to. So automated testing, but that's not really, we're not meant to talk about asserts on this. We're just talking about you know, there might be reasons for stuff being done the way they are. Now, we have successfully comprehended They're the UTRES chassis subsystem. Now, there's a reason why that UT is, from what I've heard, from the list of code bases I was given to study, when I was learning Taproot, it was the third best to second best code base. A&M is considered a bit better, and this is not necessarily it's more like in the sense of ease of comprehension. And again, I come from the school of code is read more than it's written, so that's where I put more weight than other coders, and that's just, again, depends on your priority, your conventions, and whatnot, because we can get all argumentative on how much documentation something needs, but again, I'm just gonna leave it at schools of thought, so we don't have to go to that realm, the shadow realm. So the reason why I do UTs is, one thing is like, it's just it's they're homies. We might do A&M's code base, but let's move on to now before we close for tonight. So we do not have time to go into Fang, but we are discussing some of Fang and comparing, contrasting. Because, like, as you can tell with our case, one design error that we made, and this was the old code, where is it? Control chassis, was that I wanted to focus on encapsulation as a priority, which means if a class is not messing with something, it's private. And so part of that modality at the time was to have the class manage stuff on its own. So in the old Mecanum subsystem, we can see that the constructor, this is just the 4 motors, it was a lot. There's a reason why it's now like the constructor is more like this. But again, like, this is, for me, this is like, there's a lot of heavy roasting. I'm like, I'm just gonna leave it as this ain't it. This was the earlier classes I wrote. When we go into the turret code of the old code base, which is like disappearing because when it's refactored, it gets deleted. It's a lot more modular. Like, stuff is pretty simple. But yeah, as I've said, our code base, like this one, I should have probably documented, like, trying to do encapsulation. That's why we're managing like 4 motors creations like this and a bunch of other stuff. Other than that, though, minus the initialization, as you can tell, we do encapsulate stuff a lot. We abstract stuff more, so we have like update ramps, sync logic, self-documentation, and it takes us like 2 minutes. And even with power scale, power limiter, we have a power limiter class because that's a separate responsibility. Calculating power limiting is just not the responsibility for this class. Applying it, yes. And you can tell, it provides Taproot friendly subsystem control functionality for Mecanum drive with, well, it could be any drive, so we'll fix that, but with dimensional analysis. Okay. So instead of going on, they have commands, so we'll do the commands and we'll call it a day. So command move chassis dot h++. So it takes a pointer to a chassis subsystem and a turret subsystem, has some variables, keyboard input move, the turret relative equals false, Beyblade equals false, sad. No, I'm joking. Beyblade is like a really fun mode. So this is saying sad is not a critique on the code. That's just, I like to Beyblade a lot. So in our code base, we called Shriekin because I went to A&M and they called theirs Tokyo Drift and we had to sound cool. We didn't want to just be everyone else who calls it Beyblade. You know, in terms of programming terms, I could criticize myself in terms of like going against convention, because like now every time we talk about our code base to people, we say Shuriken/Beyblade. But I mean, hey, the price of greatness, am I right? A&M also has to do that too. So okay, so initialize keyboard input move. They reinitialize the well, they don't they can't reinitialize. They assign the variable the value it was initialized with. It could be just left over from like the just refactoring stuff, but in my opinion, probably not required. You could probably remove that so it's just less mess. Because if you change this, you might think that it's going to be a new initial value for keyboard input move, but then it's going to always be 0. Now, knowing this kind of code, you probably won't need to make it not 0, but wait, vector 2f. Wait, so if I feed it, so if I feed it one value, all the values get set to that value. Okay, so like it's a 2D vector with one value. So so it gives you a 0 vector. So input move on execute is also reinitialized to 0. Oh wait, no, input move is something else. Okay. Sorry. So yaw angle, so it gets the turret yaw. So yaw is a really weird sounding word. It's just like if you're probably sitting at a computer screen, so if you turn left or right, you're rotating on the yaw angle. If you're looking up or down, that's the pitch angle. And then the third one is up, down, left, right, up, down. If you tilt side to side, it would be the roll. Actually, let me just pull up the diagrams we all like to look at if we're future engineers as kids. Pitch, roll, yaw, airplane. Oh look, it's when you do a barrel roll. Pitch when it's up and down, and yaw is the weird one, but hey. Hey, that's not cool. That's a non-standard coordinate system. Anyways, as you can see that, well, I mean, it technically still does. No, it doesn't. Wait, does it follow the right hand? Yeah, it follows the right hand rule, but anyways. This here, input spin, keyboard input, apply keyboard, has keyboard input equals apply keyboard input spin. So this is dealing with getting input, apply keyboard input. It gets a reference, which means we know that it's going to probably, well, let's see, because it's not a constant reference, so it's probably going to modify it. Let's see if it modifies it. It does modify it. So input spin is 0 if we're applying keyboard input. Oh, because this is manually doing joystick and keyboard. Okay, we're going to skip this because it's very simple. WASD, it gives you up, down, left, right, up, down, down, left, left, right, A, B, enter. You've heard of that? Yeah. Konami, yeah. You had a question? No. Okay. So, and then joystick input, right horizontal, right horizontal, right vertical, wheel, so then it kind of just maps it out to that stuff. The input move, input spin. Since we are running low on time, because I'll just kind of put into the 2 cents of what we do and why we do, and again, different modalities, because again, this is more on the functional programming end, which is all right. though you will sometimes find yourself making object-oriented programming constructs manually, because there is a book, Object-Oriented Programming in C. Do you know why C++ and object-oriented programming like happened? Where is it? This. Well, from what I could glean, people were doing stuff in C that kind of looked like this. So you have a self pointer, like a this pointer. So when you write code in a class, you can actually get a pointer to itself. You can say this. That is the memory address of the instance of that class. Because early on, compilers would literally rewrite all of the functions of this to have this and then, the rest of it. You would modify it into C code, then compile the C code into, binary. Because this did originate as a design pattern. Now, I don't know if object-oriented itself originated as a design pattern in C, but, when you have stuff like this, it is, you do start to ask, do I want to do it manually or not? And, when you get to do stuff manually, there's pros and there's also cons. I mean, who am I to complain about manual memory management? I'm a C++ guy. Unless we're using smart pointers, which we do. So we're just going to ignore this because this is basically basic input mapping. And in how we do it in our code is, so when we have mecanum command, we have Counter-Strike. Let's do Counter-Strike. I like Counter-Strike command. I hope we don't get copyrighted on this. This is too good of a name. Counter-Strike global. Yay. So it takes in, where is it? A chassis input handler. And what that does is you can configure it on key mappings and then remote mappings, and it also just gives a unified mapping, because I noticed in other code bases it was cleaner to just combine the mappings. So yeah, and then whatnot. So get rotation, rotation and stuff and blah blah blah. But you can see that it is set to a state with these constants of, what is the X translation, Y translation, what's rotation, what's, your WASD. Unless you like IJKL for some reason, we allow that. We tolerate it. That's as far as we tolerate shenanigans like that. But, and then all we have to do is Counter-Strike command. Where is it? Chassis input dot get rotation, blah blah blah, and then it does that, and so forth. So that's that's different design modalities. In the case for UT, they put it in the command. We like to abstract stuff more, so you'll notice a lot of our code looks simple, but then when you go into it, there's layers upon layers, and some people like layers, other people don't like layers. So we're a layers people. We're a layers people, just because we're some purists in C++ might accuse us, you might as well do Java, and I say no, because we're not using shared pointers for everything, because we know that's stupid in C++ and makes the performance basically like Java, because it's just but anyways, they even have an analog dead zone, blah blah blah. Fun fact, now of course it's always nice to have layers of configuration. But note, if you are making a code base, the DJI remotes do have their own dead zones, though this is actually a nice thing because you're able to, in the event that your remote does start drifting, you can just up the analog dead zone. So that is a nice one. So then we apply quadratic input ramping. Input move dot get length. So they put a ramp to the input. What that means is that it doesn't immediately give the input that you desire, from my understanding. Well, input spin, well, if it's a non-zero, then it, but anyways, we'll investigate that more. But it's some form of ramping, which means it's some sort of time-dependent thing that's designed to cushion the jolts. You can see they do namespace commands. So this is the standard. I will say I do it non-standard because OCD, it looks nicer. But technically, this is an extraneous indent. Because look, you see this, and then you see this. My brain is happier in the latter. And I know people are like, what if you have nested namespaces? Just do this. Like, don't. We did do nested namespaces, and I regret it. I fully regret it. Like, where is it? Did I think I refactored all of it to no longer use nested namespace. But we'll go into the old code version. Git status. Git checkout v 4.8.0. If we go here, nested namespace. Very bad design choice. That's on me. That's why we're refactoring. Git checkout, release, etc. So now we are at, how long has this lecture been? 2 hours. Okay, not too bad. So we're at the command move chassis, the has keyboard input. So they do stuff to process the keyboard input. They do stuff to process the joystick input. But then what else? So execute. So we have input handling this section. That's also input handling. So instead of combining inputs, they choose to do one or the other. So like which one overrides the other, which is all right. Like that's it actually might be cleaner than what we do is we combine them and then we limit the value. Next, auto align chassis to turret when moving if input is this. Calculate align correction. Let's see, calculate auto align collection. So we have the yaw angle, the chassis auto align angle, which is 3 degrees. And then chassis auto align factor is time, it's 0.5. So the input spin is set to half of the auto align factor. So we take the snap angle, and what was the snap angle? The chassis auto align angle should snap to. So I'm guessing is that when it is not spinning, so the input spin is set to nudge it back into a specific angle relative to the turret so that it's all aligned when moving. But when it is Beyblading, this gets overridden by hard-coded speed. And then rotate movement vector to turret. So if turret relative, it just means that whichever way is forward is whichever way the turret is facing. And it executes that, and it does a fun loop. And that's that. That is how you control the chassis. Sentry position, we are not going to mess with sentry. Sentry is advanced code. That is, sentry is very cool stuff. But generally, sentry code, they menacingly spin. But sometimes they can move back and forth, even more menacingly so. Sentries tend to be circular, so if they hit a wall, they don't like repeatedly bump into a wall as well, because they're usually spinning to not die, because they're automated and they're notoriously difficult to program. Okay. So that is so far standard control. So you could see that understanding a code base does take time. Reading a code base is a skill. Writing a code base is another skill. do we want to demo mode? If defined demo mode, max wheel velocity. Okay, so they have a testing mode. Constant expression, nice. I think I already mentioned uniform bracket initialization. It doesn't matter too much for primitive values, but when you do get into user-defined values such as classes, it does make a very big difference with, well, it's easier syntax, and number two, versus parenthetical initialization. It prevents wrong conversions, because some classes can automatically convert to other classes, and that may or may not be desired. So let's go to standard control. We're going to cut this at 13 minutes. Actually, let's go into our code. This should be faster. Because one, I wrote this, but number two, it's also more concise. So you can see in our main loop, we create the drivers on the stack. Maybe we should make it static. Well, no, this is a reference. We have a board, it's initialized, drivers initialize, robot. No, if I was pedantic, I would like refactor initialize into it, so main would like only be like 10 lines, but to each their own. We're not going to get too pedantic here. But since I am the one who's preaching layers and wrapping, this technically would be, and then you'd pass the reference and blah, blah, blah. But as you can tell, you just say drivers.update, drivers.motor timeout update, because like all the variables that were being updated were just drivers variables. So it's basically the same thing, but just more concise. Because as you can see, you can pretty much understand, like, initializes a driver and a robot, and then it just updates the drivers really fast. So, and then you see io.c++, h++, where is it? Oh yeah, I did remove it because I used to refactor it into their own file, and now if we go into driver, we have drivers.c++, and it's all the way here. So, what does our robot class look like? We only had one robot. This is something that has been a major refactoring. We call our robots, all our robots have planned names, and may we use the mighty fist of time to ensure that they will be named as we planned like 10 years ago. So we're Fang Robotics. If we go into Demon Slayer, Wiki, Fangs, there's Beast Breathing. There's a character that doesn't have forms. It's called Fangs, and he's this dude. But he has Fang, Pierce, Slice, Devour. We were gonna go in the order because the 7th robot is Radar in 7v7, Spatial Awareness. It's too much of a coincidence. But our 2nd robot is gonna be Hero, and Hero should be named Devour versus Slice because Hero launches golf balls and takes out half your health. You know, or I think about half your health, pretty much. 100 damage versus 10 damage per hit. So Devour, that's like... And when you get into, like, the late game, you can fire, like, 2 golf balls per second if you're even able to. So, and then with computer vision, that's, like, mega death. So, we have here... So we do not use global configurations, and as this gets more refactored, because this one obviously looks a bit more involved for initializing, because I know that global variables are nice and all, but they do entangle your code in the long run. Like these, it might look cleaner here, but when you are working with the code, when you get past 3 robots, it will be a pain to manage 3, like you're managing 4 sets of global variables. These aren't even in a namespace. So in this case, our robot class has a nested struct. And a lot of these 2 structs are actually going to be refactored away into something called a command pack, like in 2 weeks. But We're not in 2 weeks right now. We're here right now. Let's switch to let's go to the old one because we're switching to dependency injection. So I don't want to say cannibalizing. We're like doing a slow ship of thesis for replacing code. So you'll have like this while everything is that, and that's just more confusing. Okay. So pierce.hpp, pierce.c++. Let's just close it. Don't save. I guess VS Code did not like that. So we go here into, where was it? Control robots. So yeah, it was in a different part. Pierce.h++. We go here. What do you mean we can't? Yes, you can. It exists. But why does it not exist? Gimbal system. It exists. Okay, so it's tripping. It's tripping. Hold up. Let's check git status. That's why we have some submodule init, submodule update init. Okay, we're just not going to worry about it. We're just going to ignore the squiggles. Because this code does compile because this was the version used in the competition. Oh, now it wants to behave. Okay. So the reason for that is so our configuration is not like a long file, like a single file, but if you go here, there's chassis input, turret input, blah, 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 all of these. So we use structs so we can bundle things into a specific constant and, then and there. So pitch percentage per px. We have TARDIS config, shriekens feed, etc. Blah blah blah. So, and then the Pierce will pass all of these configurations. I know this looks complicated, and there's a reason why we're refactoring it, because there's trade-offs in design. We decided not to use global variables because, for example, if I'm making another robot, I would have to rename the new robot class to use different constants names. And then the question is, how do these constants get passed into, so you have the wheel distance, the wheels. Wait, I'm guessing, let me check the chassis. Where do they get the wheels constants? Standards constants. So basically you have to they're using preprocessor macro magic to get these into the robot. Oh, wait. I know where it's coming from now. And again, there's trade-offs. Like, we like to avoid preprocessor macro stuff because they don't play well into 7 robots. With 3 robots, you could probably get away with, well, you can get away with it because, So if we go here into robot constants, there we go. So they use preprocessor macro and the robot constants gets passed to everything else. It's a global variable. At least they're not using non-constant global variables, but this is not the best way to do stuff. Yes. It's a meeting for a student org. Okay. Oh, yeah. Because we locked in all the rooms out, so. Oh, okay. It's not on the schedule. Oh, gotcha, I think. Okay. Yeah, but, yeah, essentially that is what we have. We did cover some of Fang Robotics MCB. We will do that next lecture. But yeah, that is an overview into the UT robotics architecture, where we're able to use our knowledge with good programming practices, looking at the really cool stuff they did, as well as stuff that we might want to work on, and then also stuff on our end, stuff that we did good, and also stuff that we definitely need to work on our code base. Thank you for spending 2 hours and 35 minutes of your time, and have a nice evening. Yay.